We often think of the world as solid and continuous. When we touch a piece of metal or a smooth pane of glass, our senses tell us we are interacting with a uniform substance. But if we could zoom in, the familiar world would begin to dissolve into something unrecognizable. For centuries, atoms were treated as a mathematical convenience, a way to explain chemistry without actually proving they existed as physical objects. The reason we couldn't see them wasn't just a lack of magnification. It was a fundamental conflict between the nature of light and the scale of the universe. The problem lies in the physics of light itself. Visible light is a wave, and waves have a physical width, known as a wavelength. Even the shortest waves of violet light are about 400 nanometers wide. An atom, by comparison, is roughly 0.1 nanometers across. Trying to see an atom with visible light is like trying to measure the fine grooves of a record using a thick wooden log. The light wave is simply too fat to bounce off the atom. Instead, the light just washes over it, leaving the atom invisible to even the most powerful optical microscopes. This barrier is known as the diffraction limit. In the late 19th century, physicist Ernst Abbe calculated that we could never see anything smaller than half the wavelength of the light we were using. This meant that the atomic world was effectively locked away from human sight forever. We reached a dead end where better glass lenses could no longer help us. To go deeper, we didn't need a better microscope. We needed a different kind of light entirely, something with a wavelength thousands of times smaller than anything in the visible spectrum. The breakthrough came from a seemingly unrelated discovery in quantum mechanics. In 1924, Louis de Broglie proposed that particles, like electrons, could also behave like waves. This meant that if we accelerated an electron to a high speed, its wavelength would become incredibly short, far shorter than visible light. While a photon of light is bulky, a fast-moving electron is needle-sharp. This realization changed everything. If electrons were waves, we could theoretically use them to build a new kind of microscope that could resolve the tiny details of the atomic landscape. But using electrons presented a new challenge. How do you focus a beam of particles? You can't use glass lenses because electrons can't pass through glass. They would simply be absorbed. Instead, scientists turned to electromagnetism. Since electrons carry a negative charge, their path can be bent by magnetic fields. In an electron microscope, large copper coils create precise magnetic lenses. These lenses don't refract light. They use invisible magnetic forces to squeeze and focus the electron beam into a point so fine that it can interact with individual atoms. Inside the column of a modern electron microscope, the environment is closer to outer space than to a laboratory. All the air must be pumped out to create a near-perfect vacuum. If an electron hit a single molecule of oxygen or nitrogen, it would scatter and ruin the image. In this silent void, a high-voltage filament fires a stream of electrons downward at nearly the speed of light. They accelerate through the magnetic lenses, gaining the energy needed to pierce through a sample that has been sliced thinner than a virus. When the electron beam finally hits the sample, something remarkable happens. Some electrons pass straight through, while others are deflected by the nuclei of the atoms in the specimen. This creates a shadow-like image on a sensitive detector at the bottom. This is transmission electron microscopy, or TEM. The result isn't a photograph in the traditional sense, it's a map of density. Darker areas represent places where atoms are packed tightly together, blocking the beam, while lighter areas show where the path was clear. The images we see at 10 million times magnification are haunting. At this scale, matter no longer looks solid. We see the lattice, the orderly grid-like arrangement that atoms form in minerals and metals. Individual atoms appear as small, fuzzy spheres of probability. They don't have hard edges. They look like soft clouds of light. This is the reality of the micro-world. It is mostly empty space, held together by the electric tension between these tiny, ghostly points of matter. It is the first time in history we have seen the foundations of our universe. Until recently, these images were often slightly blurred by imperfections in the magnetic lenses, a problem called spherical aberration. It was the equivalent of looking through a foggy window. However, in the last 2 decades, aberration correctors, complex computer-controlled magnets have allowed us to sharpen the focus to the picoscale. We can now see not just where an atom is, but how it shifts and vibrates. We are beginning to watch the dance of subatomic particles in real time, observing how a single atom's position can change the properties of an entire material. As we move into the future of pico-imaging, the line between physics and chemistry is disappearing. We are no longer just observers of matter. We are learning to manipulate it atom by atom. The electron microscope has taken us on a journey from the familiar, solid world to the edge of reality, where matter looks more like a ghost than a stone. It reminds us that everything we see, the stars, the earth, and ourselves is built from these tiny, rhythmic vibrations, finally brought into focus by the very electrons that keep the universe together.
If you'd like more videos like this, you can subscribe and come back to Brief Stories anytime.